do. So the title is Sensitivity and Repeatability of Hyperpolarized NMR in Dissolution-DNP Experiments. Really the talk has two parts, and the first one is about sensitivity essentially of normal NMR experiments. And then the second part, we will look at developments in hyperpolarized NMR, and more specifically dissolution-DNP type experiments, and even more specifically the bullet-DNP experiments that we run in our lab. Just to give you a flavor, this is a picture of our lab. And so this is basically what we need to do our hyperpolarization experiments. And I'll get into the details later, but for now, you can take from this picture that there is a fair bit of complexity. And so the question is really, is it worth it? And to know whether it's worth it, we need to first understand what actually is the sensitivity, or at least if we want to do this hyperpolarization to enhance sensitivity, then we need to first understand the sensitivity of a regular NMR experiment, and then we can see how much we may be able to gain with hyperpolarization. Okay, so part one is sensitivity in conventional NMR, and with sensitivity, what we mean typically is signal to noise. And so the question is, what is the signal to noise ratio? So as I said, there's next to nothing new in this talk, and you can read about the signal to noise ratio. There's this classic paper by Holt and Richards, and we'll get back to that during this talk. There's also the book, the classic textbook by Slichter. And all we have done recently is we've extended this work to the frequency domain. And that's actually where the signal to noise ratio is usually taken. So if you run an experiment with topspin, let's say, and you type CNO to find out what the signal to noise ratio is, what it actually does is it calculates the ratio of the peak height here and the root mean square of the noise. So here I've simulated this. So you see the noise here, and this is a signal with an amplitude of 100. So this would be a signal to noise ratio of 100. And then when you have a signal to noise ratio, when you're down to 10, that's what's called the limit of quantification typically. And then with a signal to noise ratio of 3, there's actually a peak here. And you can essentially, well, that's just at the edge of being detectable. I would probably not say that's a signal if I saw this on the spectrometer, but that's basically where the limit is. So those are the numbers. And this is the signal to noise ratio. And what we do now, we basically calculate the signal to noise ratio from first principles. So we need to first understand where the NMR signal comes from. And that comes, of course, from the magnetic moment of the spin. So when you have a spin, you have a magnetic moment, and that magnetic moment mu here is proportional and parallel or anti-parallel to the spin I. And the constant here is the gyromagnetic ratio. If it were just that would be a bit like a bar magnet. So bar magnets have magnetic moment, and they interact with the magnetic field. So if you put them in a magnetic field, it's a bit like a compass needle. If there wasn't any friction, then that compass needle would oscillate about the field, like so. Okay, but of course, the situation is a bit different because the spin is an angular momentum, and the angular momentum is also conserved. So then the situation is more like that we have a magnetic moment that precesses about the magnetic field with a Larmor frequency. So that looks like that. We have this precession here on this cone. And now we see that we have a transverse component that would oscillate here. So what we can do is we could put a coil around this x-axis here, and then we would get a changing flux through that coil, and that is something we can pick up and record a signal. That's Faraday's law of induction. Okay, now the signal of a single nuclear spin would be, I mean, putting quantum mechanics aside, the signal of a single nuclear spin would be too weak for detection, so we use more than one spin. So that's where the magnetization comes into play. That's just the density of spins multiplied with their magnetic moment and the polarization. So if you integrate this over the sample volume, you basically just get the sum of all the magnetic moments. And if they were all lined up, then you get a correspondingly bigger signal. And that would be the case that the polarization would be 1. And then the magnetization is maximal. On the other hand, if the polarization is 0, then all these magnetic moments are basically pointing in completely random directions, and then you don't get any signal. So the question, of course, is now how much polarization do we normally have? And that's where the Boltzmann distribution comes into play. So this is almost always the case that the nuclear spins are quantized along the field that you apply, your B0 field, and then these states are populated according to the Boltzmann distribution. And the mathematics of that are like such that you can work out that the polarization is given by this expression, which in the high temperature approximation becomes delta E over 2kT. Okay, if you plot this tangent hyperbolicus here as a function of temperature at a normal field, in this case here we have it at 6.7 Tesla, you see these dependencies. So for carbon and proton, you have a completely linear range here. And for protons in particular, at 300 Kelvin, you have a polarization of only 23 ppm. For the electron, we'll get to the electron later. I will not talk about DNP, but what we use in DNP is, of course, the electron polarization, which at 1 Kelvin here is essentially unity. But anyway, under ambient conditions, we have a very low polarization of only 23 ppm. So if we look at the man, we think we must have seen it coming. He must have seen it coming. Okay. So let's ask us anyway, how much magnetization do we have with these polarizations? So here I run this example for water. I could put the concentration of water 55 molar, and then we have 2 protons. Then we have the gyromagnetic ratio. We have a spin 1/2, and we have a polarization of 23 ppm. If you multiply all these numbers, you get 20 milliamperes per meter. That is essentially the biggest magnetization that we deal with in magnetic resonance. That would be the signal of a pure water sample. By comparison, at the lower end, if you do drug screening, you work with concentrations essentially so low that you can still detect them in a reasonable time, and that works out typically as 200 micromolar. And if you just scale this number accordingly, then you get a magnetization of 40 nanoamps per meter. So you see there are almost 6 orders of magnitude between these two magnetizations. And the question is, of course, what voltage and what signal to noise will we get from these magnetizations? So to do that, to answer that, we need Faraday's law of induction. Basically, what happens is we take this Z magnetization and we turn it into the XY plane. And now it precesses. And as it precesses, we have a changing flux. And this changing flux then gives us an induced voltage according to Faraday's law of induction. And now the question is, okay, how should we design the coil so that the signal to noise becomes maximal? So here there's nothing about the noise, but we see in a moment that we always have noise when we have a conductor. Okay, and for that we look at this principle of reciprocity. So here I start, and what I have here, I have my coil. That's just a piece of wire, and now there's current I running along the wire. And the current I running here along this length element dl creates at a displacement r a magnetic field contribution dB or dB1. Okay, and if I want to know the total field, then I just have to integrate along the entire wire. So I integrate along all these length elements, and then I get B1. Okay, that's what I have here, and I can change the L and R in the cross product, and then I get a minus sign. And if I divide by the current, then I get B1 over I. That is given by this expression here. Now, I can also ask the reverse question. What happens if I have a magnetic moment at this point where I was just calculating dB here? And now, so if I have a magnetic moment here, then at this point, I get a vector potential from it. So A is called the vector potential. That's an electrodynamics thing. And this is given by this expression here. And I can, again, let me get this out of the way. Now here, I have R prime, which is this vector, and you notice that r prime is just the inverse of r. So if I write it in terms of r, then I get a minus sign here. And now I can calculate the magnetic field from the vector potential. That's just the curl of the vector potential. And so I can calculate my induced voltage here using the curl of the vector potential. And now I have Stokes' theorem. So I can rewrite this integral over the area of the curl. I can write as an integral along the curve, along the wire of the vector potential. Okay, and now I substitute the vector potential for A, so that's my m cross r here. And I rewrite this now like so. So I basically do a cyclic permutation here, m cross r dl. I move these counterclockwise, so I get r cross dl dot m. Okay, now notice this thing here, now colored in green, is exactly what I have here on the left-hand side. Okay, so I can rewrite my induced voltage as minus d over dt, b1 over I times m. Okay, so that's in essence the principle of reciprocity. I can take it one step further. This would be here on the right-hand side. This would be for a single magnetic moment. And if I want to have that for all the magnetic moments in the sample, then I just need to integrate over the magnetization. Okay, so that's now written here. And if now I assume that the magnetic field, the B1 field is constant and the magnetization is also constant, and I furthermore assume that the B1 field, well, this is just confined to the coil, then I just can replace this triple integral here just with B1 times m times the volume. Yeah, so this is what I have here, B1 times m times the volume. Yeah, and the omega here I get because I still have to take the derivative. Okay, so this is now my induced voltage. It's B1 over I. It scales with B1 over I. And so that means that if I have a detector, which when I apply the RF pulse gives me a lot of B1 for a given current, then by reciprocity, I will also get a lot of induced voltage or a big signal. And so this gets a frame. This is the principle of reciprocity. But we are not done yet because we have the current here, and we now want to express the signal to noise, not with the current, but with quantities that we can readily measure in the lab. And these quantities are the B1 field that we get from the notation experiment, the power, which we can just dial in or measure easily, and the Q. And I will not talk during the lecture about ways of measuring the Q. If you want to know and there's time at the end, then we can discuss. I have 2 slides at the end where we can have a look at this. Okay, but now, let's get rid of the current here. So if we have an inductor or coil, the NMR coil is an inductor L, and we have current running through it, then that stores energy, which is 1/2 times L times I squared. Okay, now that energy is really the energy of the field, and this I can write again as this integral. And now if again I assume that my field is confined to the coil volume, then I can just say, okay, this is the magnetic field squared times the coil volume. Okay, so I can solve this for the magnetic field. And now the other thing I need to put in here is this expression. So I know that basically when I apply an RF pulse, then I apply a certain power, let's say 100 watts. So this power is dissipated as electrical energy, and the dissipation is of course 1/2 R times I squared. So I also have this, if I know the power, then I know that 1/2 times the coil's resistance times I squared, that is my power. Okay, so I can also rearrange this, solve for the current, and now I can insert what I calculated here for the current into my expression for the magnetic field. So now I can write my magnetic field as 2 mu 0 LP divided by the coil's resistance times the coil volume. Okay, so now we introduce here the coil's Q factor, Q, that's omega L over RC, and we can then write the magnetic field like this. And we do that because the Q we can readily measure. The inductance is not, let's say, so easy to measure, but the Q we can measure. And so then we get this B here, that's 2 mu 0 Q divided by omega times the coil volume and the square root. Now, the magnetic field we calculated in this way is the magnetic field that's just oscillating in the coil, and it's linearly polarized. And in NMR, what we need is the circularly polarized part of that. And that is just 1/2 of the linearly polarized field. So my B1 is then given by this expression here. Okay. Now, yeah, one side note here is if you have B1, if you have this expression, you can also calculate B1 over square root of power. And, or you could also say, okay, what's my pi-half pulse duration over square root of power? And basically, the shorter the pulse duration is, or the stronger B1, then the better is your probe for a given coil volume. So if someone tells you they have a very sensitive probe, you can always just ask, okay, how much B1 do you get per square root power, and what's the volume? And then you can immediately put a hard number on the sensitivity of that probe. Okay. Now, if we insert this this expression for B1 into the principle of reciprocity, then we get this expression here. So we see that our signal voltage or our voltage scales like that. And I've also introduced here eta, what's called the filling factor. So that's the ratio of the sample volume and the coil volume. So the coil is always bigger than the sample, right? Because it's wrapped around the sample. And it can be a tight wrap, or for example, if it's a solenoid, you have a good filling factor. But if you have, say, sometimes maybe you have a larger coil, that would be the case also if you have a cryoprobe, the coil would become a bit larger. And so the filling factor would go down a bit. Okay, so that's the signal. Now let's look at the noise. So the noise, there's actually, that's been known for almost 100 years now. The noise is Johnson noise, and that's just given here by square root of 4 times the coil resistance times K times the coil temperature times the bandwidth. So for example, if you record an NMR spectrum, you may want to record over a bandwidth of 1 megahertz or so. So then this bandwidth would be set to 1 megahertz. And that would determine how much noise you have in the time domain. Okay, so now we know the noise, we know the signal, so we can calculate the signal to noise ratio in the time domain. Okay, because we calculated the signal in the time domain and also the noise in the time domain. So the signal to noise ratio then is this. So we have this funny expression here that again depends on the bandwidth of our receiver. And of course, it depends also on how much magnetization we have and on the filling factor, on the Q, and so on. But we know that in the frequency domain, I mean, normally when we record NMR spectra, we don't really pay a lot of attention to how we choose the bandwidth. We just choose it wide enough so that we can record the signal, and that's also perfectly fine. And that is so because what we need to look at is the signal to noise ratio in the frequency domain. So how do we calculate that? Okay, for that we just need to do a Fourier transform of the noise and the signal. So the Fourier transform that goes like this: if you have samples in the time domain with a small x, xm, then you can calculate your coefficients in the Fourier in the frequency domain like so. Yeah, this is the Fourier transform, the discrete Fourier transform. Okay, and there's a Parseval's theorem which states that the variance in the time domain is equal to 1 over n times the variance in the frequency domain. Okay, so in other words, if you have a root mean square noise of the noise voltage in the time domain, then you get square root n times this value in the frequency domain. This is also clear if you double the number of samples. So if you for example just double the acquisition time and keep everything else the same, then your noise increases by square root 2. The same as if you do, instead of 1 scan, you do 2 scans. So you signal average for, if you record 2 averages, then you would also get an increase in the noise by a factor of square root 2. Okay. Now for the signal, we choose our signal such that the calculation is easy. So we choose it to appear on resonance, so that k is equal to 0. And we also choose it to decay exponentially with a, this would be the spin-spin relaxation rate, R2. So then I can write my signal as such that it's the voltage at the beginning of the FID, and then it decays exponentially. And here m is my mth sample, and I have the acquisition time, and here I have the number of points in the free induction decay that I record. Yeah, and I can now take this m here and write it into the exponent like that. Okay, then I can really calculate the Fourier transform of this, and the Fourier transform gives me my NMR signal intensity here. It's this expression. Yeah, I just have to sum over all these points, and now I can, if I choose my acquisition time long enough, then my signal will have decayed to 0 when I approach n here. And then I can replace this sum here with an infinite sum. And if I have that, then I can evaluate this sum using a geometric series. So that's this series here. If you have q, infinite sum over q to the power of n, and q has to be smaller than 1, then that sum is 1 over 1 minus q. So from that, we get the signal in the frequency domain, which is just my time domain amplitude divided by 1 minus q. And now here, here I expand now the exponential. I assume that this is a small number, which again I can always do by just choosing n large enough, and then I get this value for my signal intensity in the frequency domain. Okay, good. So now we have the noise in the frequency domain and the signal in the frequency domain. So we can calculate the signal to noise ratio in the frequency domain, and we get this expression. And you see here that this now depends on the acquisition time. Yeah, that's indeed so. So you shouldn't acquire a lot more points after the end of the FID, right? Because then you just record noise and your signal to noise will just go down. But then also you don't normally pay huge attention because you just use apodization after the fact. So let's briefly look at the effect of apodization. So let's say we use apodization with a line broadening of RA, A for apodization. Then the signal goes down, and we just have to replace R2 essentially with R2 plus RA. Okay, and for the noise, it's a bit more tricky, but basically you just look at how the noise power is reduced. So here, this is a fraction of the noise power. Here I integrate over 1. And here I integrate over the exponentially decaying noise power. So I get this ratio. And then I scale the noise as well. And if I scale both the noise and the signal with this apodization, then I get a new signal to noise ratio, which looks like that. So this is also a complicated expression, but now I can use apodization, which is equal to the observed relaxation rate. Yeah? So if you have this is also what you do in practice. If your signal decays and has, say, a line width of 2 Hertz, then you would also use 2 Hertz of apodization to get a good signal to noise ratio in the frequency domain. So you would use RA equals R2. And if you do that here in this equation, then you get this one. So you get a signal to noise ratio that's given by this function. And now that's a pretty useful expression, I believe, because here you can see what really matters. So what really matters is, of course, your magnetization, your filling factor, your coil volume, and your coil's quality factor, and then also your shim, if you will, yeah, or how sharp is your line, how long does your FID last? Okay, so let's look at let's use this equation and evaluate it. So what I've done here, I again take a field of 6.7 Tesla, Q of 100, R2 of 2 Hertz, and a 5 millimeter probe with a filling factor of 0.5. And now if we look at the signal-to-noise ratio for water, that was the big magnetization that we looked at in the beginning, we get a signal-to-noise ratio of 10 to the 7. So no need to do signal averaging here, okay? Now, if we go down to the drug screening setting, it's 200 micromolar, then our signal-to-noise ratio after a single scan would just be 10. And notice these are very forgiving circumstances because I said I have a singlet here. Yeah, if I have J couplings to other spins, then of course my line splits and the signal-to-noise goes down. So here I already have a fairly low signal-to-noise ratio, and I can boost it though by doing signal averaging. Yeah, if I record 10,000 scans, then I can boost my signal-to-noise by a factor 100. Now, if we go still lower towards 1 micromolar, then we calculate a signal-to-noise ratio of 0.1. And if we average 10,000 scans, then we have a signal-to-noise ratio of just 10. So still a meager number. So that here is essentially the realm where this whole hyperpolarization thing becomes quite interesting. At 1 micromolar, maybe 10 micromolar, thereabout, that would be cool if we can do hyperpolarization to explore these concentration regimes. Okay, so how do we do DNP? So this is the second part of the talk now, essentially, and it starts with a very brief history. And the first setup that we used to do bullet DNP works like this. We take a sample, we place it into a magnet and liquid helium and bring the temperature down to 1.5 Kelvin. The sample is the red thing here, and it sits in a bullet, which is that white thing around it. It's a plastic capsule. And then we polarize it by shining microwave light onto it. And then once it's polarized, we shoot it out through this tunnel here. You see a solenoid. The tunnel is energized. And then it arrives in the second magnet, and there we have a solvent reservoir. And this is made such that the bullet, this plastic capsule, stays here. It is retained, but the sample can go through this constriction, and that is dissolved. And then it is pushed into the NMR tube, and then we record the NMR spectrum. I'm sorry. Yeah. Here is the depiction of that same process by our PhD student, Dima. And I should say that we are looking for 2 more PhD students. This is the result of that process. So that's what we published in 2019. So this works. We have nice polarization levels of 30% in the liquid. But look, we are starting with neat pyruvic acid. I mean, that's a very well-established test system, but neat pyruvic acid has a concentration of 14 molar. And then in our experiment, we dilute this tenfold, so we are at 1 molar. So you absolutely don't need hyperpolarization to record these spectra, obviously. What is also striking here in this data set is that the lines are very, very wide. So look, the lines are almost like half a ppm wide. And of course, so that is a very fast R2, and that also costs resolution and sensitivity. So that was the state of affairs in 2019. Then we basically copied an idea from Christian Hilty, and we used back pressure. So what happens is when you shoot this bullet into the water, it makes a big splash, and you have lots of tiny bubbles. And these bubbles, they basically cause susceptibility. Well, due to their different susceptibility, they cause variations in the magnetic field that the sample or the spins experience. And that gives you line broadening. So if you apply pressure, you can make these bubbles smaller, you can redissolve some of them, and then you recover some resolution. So we basically implemented this technique at KIT, at our new institution. And you can see here in gray, this is the data from Southampton. That's the spectrum I was just showing earlier. And in blue, you can see the new spectrum with improved resolution. Okay, but we are still at 1 molar pyruvate here. Yeah. So now finally, last year, we finally made progress. This is work from Pooja Naval, our PhD student, and she did the following. She took pyruvate, not the neat pyruvic acid that we normally use, but she took minute quantities of sodium pyruvate and dissolved them in a glass-forming agent with partially carbon-labeled DMSO. And so this carbon-labeled DMSO would facilitate spin diffusion, and it would also facilitate spin diffusion to the sodium pyruvate. And then we would dissolve that, and what you can see here is a spectrum, and this line here, that is the signal that she was able to record. And this is now a concentration of 700 nanomole. So we were basically going towards the lower limits. We also did here, this was work together with Alva Gossard and Niels Lorz at ETH. So we also, to boost the sensitivity a bit further, we take the carbon polarization here and transfer it to these methyl protons, and only then do we do the readout. And that's how we were able to record here the signal from just 50 or so nanograms of material. Okay, now you can see a few more data sets here. This is again the 700 nanomolar. You can push it a bit further. At 250 nanomolar, you just about still see the signal. And then at 100 nanomolar, we can argue whether there's a signal or not. But certainly nanograms of pyruvate are detectable. And you can also do that for amino acids. If you have amino acids with a C-alpha carbon label, then you can do essentially the same trick. So that's shown here. I think these are low micromolar concentrations. Okay, that's very nice, but and I think it's a very sensitive way to detect pyruvate. But of course, here we need the carbon label to begin with. So in other words, we need to already know what we have. And so the obvious question is, what about protons? What can we do with protons? So we also actually did an experiment together with Jeffrey Bodenhausen's group at ENS Paris last year or we published it last year anyway, with protons. So this is not the subject of this talk. This is long-lived states. But what we observed here is that you can basically achieve 100-fold enhancements on the protons. Okay, so now if you think, okay, 100-fold enhancement in signal to noise, that's nice, but it's again that number where I can just do 10,000 scans and I don't have to do all that hyperpolarization jazz. So it's not safe for some applications like these long-lived states where you have other benefits. It's not really useful for many sensitivity applications for proton NMR. So we have the same question again. What about protons? What can we do? Okay, and now this is where automation, I think, has made a difference for us. The story, in my view, is essentially this. So, of course, we've been trying to do proton hyperpolarization for quite some time, but we were not quite able to systematically study the effects that would give us a strong proton hyperpolarization. And that's due to variability in the system. So if you run DNP experiments manually, then you have to be aware that a human is not a machine. So on the one hand, of course, you're limited in the time that you can use the machine, but then also the machine is, it has a bit of its own life. So for example, there's this helium level inside the sample space that is difficult to control perfectly. And so every time you run an experiment, the machine might be in a slightly different state, and your outcomes might be slightly different. But if you have automation, then you can program the machine to do the same thing over and over and over. And latest after a few scans, the machine will go into a quasi-steady state. And this can help greatly in studying such processes. So I will show you now how we do this in our lab. So this is again the messy lab picture. And you see here on the left hand, there's a fridge and there's what we call the autoloader. And that's where we prepare the bullets. You see in a moment how that is done. And once they are prepared, we shoot them through these cables here. And they go all the way to somewhere over here. And that's where our polarizer is, this green can here. Then we polarize them. And once they are polarized, we shoot them out of this green can into this white can here. This is our liquid state NMR machine. And then we record the spectrum. And then we clean the system. So we get rid of the old bullet and we get rid of all the solvents and we repeat. Okay, so here is a render that Masoud prepared of this machine. And the new thing, let's say, is here on the left. This is what sits in the fridge. So you can see here, there is a moving arm and there is a tube. And in this tube, you have bullets. And so the first step is that this arm moves forward such that one of these bullets can drop into this little hole here. And then once that has happened, then we can fill the bullet with liquid from this well plate. It's a 96 well plate. And then, and this is something we learned the hard way, we have to freeze the material while the bullet is in position. So any attempts of ours to move the bullet with liquid, being liquid, always led to a lot of frustration. So at the end, we decided we freeze it in position. So we do that by running liquid nitrogen through these copper tubes here. So these copper tubes are connected internally in this aluminum piece here. And that freezes the bullet. And then once it's frozen, we move this arm to a third position. And from there, we can now shoot it through this tube here. So it goes out at the bottom, and then it goes all the way here to the switch. You can see it arriving here. The switch would be shifted to the right, and then the bullet would go all the way into this space here. This is an airlock, so we can close now these valves, and then we can replace any nitrogen or air in here with helium. And once we are sure that there's no air and no nitrogen, then we drop it into the polarizer and polarize it. And then once that is done, then, and this we've published already a while ago, we shoot it out into this injection device here where we dissolve it, and then we record the NMR spectrum. Okay, I like to show you this machine that prepares the bullet. So you can see this here. You have this pipetting arm. And here you have this moving arm. So first, this moving arm will now place a bullet into this receptacle, this aluminum block here. And then it will get filled. Okay, so now it's moving here. You can also see a top view. Now the bullet will be in there. And then the arm comes, picks up some liquid from the well plate. And then it will dispense it in this into the bullet. Like that. Okay, and then once the dispensing is done, we run liquid nitrogen through these copper tubes. And that's a bit fast forward. That actually takes a few minutes for this copper block to cool. So we just skip that, and then we shoot it out. And then it's done. And we put the next empty bullet in. Okay, so that's how that works. Okay, and now we can look at the results. So here, these are, so we have a little thing in our group. So whenever a factor 2 is achieved, then I invite the group for some kind of dinner. And so we only had the 32 dinner last week. And so right now we are not significantly above 32 because the group only makes progress after the dinner. That's what I found out. So here we have actually 33 experiments. These are 33 build-ups. Measured essentially in a single experiment over 24 hours overnight. And you can see that the consistency is, in my view at least, very good. So the build-ups produce almost perfectly initially, and then there is maybe a slight tendency towards somewhat slightly lower intensity here. But what is remarkable here is that it worked at all. Yeah, so you have 33 times a new bullet is placed into the machine, and it's ejected, the liquid state is recorded, and so on, and no failure. Okay, so the liquid state signal looks like this now. So that's not as perfectly reproduced. You can see that you have fairly repetitive signal intensities, but there is maybe a variability of a factor 2 or so, and sometimes you have outliers where maybe you have a big bubble in the NMR tube. So those experiments you would need to repeat. You can also see this in the line width. So the line width is also reproducing fairly well, but you can see that sometimes you have substantially wider lines, which again we attribute to bubbles and inhomogeneities. Okay, so that works. So that's quite nice. We found that quite nice. And now the question is, okay, what do we do with it? So one of the first things that we did is we looked at the concentration of the temp hole in the DNP sample and the proton enhancement that we would get as a result. To be fair, so actually when these long-lived state experiments that we did with the Paris team, in those experiments already Anna Sonnefeld suggested that we should reduce the radical concentration from the 50 millimolar that we were using. And I think we went to 40, if I recall correctly, and we indeed got more. But now we use this machine to systematically study the proton enhancement that we would get as a function of temporal concentration. And this is done for different build-up times here. So these are experiments that Dima did. And what you can see is that 50 millimolar is not at all the optimal concentration if you don't look at the solid state polarization, but really at the resulting liquid state polarization. So you would rather use something like 25 millimolar here. Okay, so that's lesson learned. Now we looked at the tunnel current. This has also been a question of ours that we had failed to answer in the past. And we see that with this 25 millimolar concentration, if we increase the current, we just get more and more enhancement. So at a 40 amperes current, that would make a field of approximately 40 millitesla. We get an enhancement of 400, and you see it's very tempting here to increase that magnetic field further. Okay. Now, sorry. There's one. So now we know how to choose a radical concentration, and so we decided to look at a molecule and see whether we can detect it without any carbon label. And so this is where we are right now. This is tryptophan, a molecule that we want to use for binding studies. And here you can see the spectrum that we recorded with a final concentration of 20 micromolar. So at that concentration, we can right now easily see the tryptophan. We did one more thing. So this was all these experiments so far were done in a DNP juice, which contains D2O and protonated glycerol and water. Yeah, so water, glycerol, and water, D2O, glycerol. Yeah, 1 to 3 to 6, and the glycerol was protonated. And there's actually a paper from Arnaud Common's group from 2013 where they replaced the glycerol with deuterated glycerol and got substantially stronger carbon enhancements in the liquid state. And there's probably more references, but so what we did is we replaced the glycerol with deuterated glycerol and repeated the experiments. And these are the enhancements that we then got. Again, this has been done by Dima and Kayum. So now we get here proton enhancements of, this is actually 2,100 in the first scan. This is the blue line here. And then if you wait a second for the second scan, then actually what happens is your enhancement obviously goes down because the signal decays, but your resolution improves. So this is something that we see that we see often, that the resolution improves, and so you actually have the same peak height here. Anyway, so these enhancements here are well above 1,000, and that should enable us to record proton spectra of unlabeled substances well in the low micromolar regime. Okay, with that, I'd like to conclude. So first, I've shown that we can calculate signal-to-noise ratio in NMR in the frequency domain from first principles. And at concentrations of the order of 100 micromolar, give or take, conventional NMR starts to struggle. And I've presented you a scheme for observing pyruvate at concentrations as low as 250 nanomolar. And we can today observe molecules, protons at 10 micromolar without labeling. And also, bullet-DNP has been automated. And so we can run dozens of experiments in a single day. Not every day, but it's rather frequent. Okay, with that, I would like to thank various people here. So at KIT, Pooja Naval did the work on the pyruvate. And then here, Dima should also be in bold. So Dima, Masoud, Karel, and Kayum, I would like to highlight for their work on the autoloader. And then we had the collaboration with the ENS team. So that's Jeffrey, Kirill, Anna, and Eike on the long-lived states. And the ETH team, Alva Gossard. We worked with Alva Gossard a lot for the ENAPT and detection of pyruvate. And actually, Sami Jana also contributed a little bit to that project. And I would like to acknowledge these funding bodies. And I would like to thank the team again. I should say briefly, so here we have Masoud and Dima and Kayum, who did the work on the autoloader with Karel in the back. And Pooja Naval did the work on ENAPT pyruvate. And that's it. Thank you.
Thank you, Benno, for the fantastic talk. Thank you very much. Now it's time for questions. And I will start with my question. Benno, so you said you figured out with the help of Anna that the optimal radical loading of Temple was 25 millimolar instead of 50. So when you say the throughput is you can do a dozen of experiment per day, do you use 50 millimolar or 25? And if it was 50, how did you quantify how much the build-up time in the solid state is slowed down using 25 millimolar?
So we use 25 now, because if you look back at these data here, for 50, I mean, maybe the buildup is faster, but what you get at the end, so not in the solid, but what you get at the end is really much, much less than what you get at 25. I think, even at 25, the buildup is reasonably fast. So it's not that it would take 2 hours then or so. I don't believe that we have these curves in a comparison. So I'm pretty convinced that we've measured these buildups at the different radical concentrations because we did these experiments here. But I don't have a plot now, so I can't tell you exactly how the buildup times develop with the radical concentration.
Okay, so you explained the decrease in enhancement because of the paramagnetic relaxation occurring during the transfer, or is there?
Yeah, that's an interesting question. Yeah, so yes, we believe it's during the transfer because we also see this dependence on magnetic field during the transfer. Yeah, so we see that we are clearly losing there because we don't have enough magnetic field. But what exactly the mechanism is, how fast it is, I mean, these are things that we don't fully know.
Thank you. Okay. So there is a question from Cass. What is the future grand plans for the automatic loading system?
Yes. So the thing that we really want to do with it is drug screening. So this ERC project that pays our bills and our salaries is set up to do drug screening. And so this is where we are going. So we are now preparing measurements with mixtures. And then the next step is to bring in targets, so a protein that these small molecules then can bind to and to observe that process. And the beauty of that would be is actually if you, with NMR, you can measure the binding strength of a ligand, but only in a range. So this binding strength is measured by a binding constant, which is given as a unit of a concentration. So A weak binder may have a binding constant of, say, 200 or 500 micromolar. And that's the binding constant you can measure with NMR because that's the concentration that you can observe with NMR. Now, as the binding gets stronger, so you basically go more towards a proper drug, then the binding constant becomes smaller. So then you have maybe a binding constant of 1 micromolar, 100 nanomolar, and so on. And if you want to determine that binding strength, then you need to be able to detect this small molecule at that concentration. And this is something that we believe we may be able to do, but that would be probably impossible with conventional NMR.
That's when hyperpolarization comes at play. So about this collaboration with Alvarta on drug screening, what's your strategy then to measure the bindings? You want to use a single scan CPMG or measure a T1 decay? What's your strategy?
Yeah, so there are actually various so-called contrast mechanisms, yeah, for the binding. So a CPMG type is possible, and that's high up in our books. There is also a T1 evolution that actually has an interesting field dependence. So that's also something we are looking into. Yeah, and then we see what else comes up.
There is a question from Jeffrey Bodenhausen. So after dissolution, the concentrations of tempo are much higher in bullet experiments than in traditional liquid state dissolution DNP, because the dilution is, say, 1/10 in the former case and 100 in the latter. Okay, so that was not a question, that was, I think, a remark.
Yeah.
Thank you, Jeffrey, for the remark.
So maybe I comment anyway.
Yeah.
If I may. So in these experiments here, actually the dilution is 20-fold. So we use a 40 microliter bullet volume and 800 microliter of liquid. That helps us with filling the NMR tube reliably. So it's a little it's not as bad as it might be with the radical concentration. And I think moreover, like if you have protons like these fast relaxing on the molecules, then we see the relaxation due to the radical, but it's not the absolute dominant thing. So even if we reduce the radical concentration, we see a modest reduction in relaxation rates, let's say. But it's not the primary thing that we feel we need to work on. But of course, there are interesting ways to deal with that problem. Yeah.
Okay. There is another question from Diganta. How fast does the bullet travels in the transfer line? Do you have a value of speed?
Yes, this is something we measured early on. Actually, we measured that before we did DNP. So because we were transferring samples for other purposes. And we noticed they were traveling quite fast. So we took 2 optical detectors and we mounted them on a piece of aluminum 30 centimeters apart, and we measured, and it took 4 milliseconds, if I recall correctly. Ta-da! So it works out to roughly 100 meters per second. Yeah, it's a bit slower if it goes around a bend, and it maybe is a bit faster if you increase the pressure. So we use 8 bars here to push the bullet, and then you get these speeds. And that translates to something a little less than 100 milliseconds to go from the magnet, from one magnet to the other.
So you use helium pressure to drive the bullet?
Yeah, you have to, because everything else would freeze, right? You have to push it out of the cold space of the magnet, and yeah. Okay.
There is a question from Asif too. So Asif didn't quite understand why proton bullet-DNP is more challenging than carbon bullet-DNP. You know, in this reverse inept project that you showed, why did you require the reverse inept, and why not directly hyperpolarized proton?
Yeah, good question, Asif. So it's just something we observe, right? So when we do carbon hyperpolarization, we fairly easily get 40% polarization in the liquid state. But with protons, it's much less. And I think now we understand, for example, that we have not been using anything close to the optimal radical concentration, because we did use values around here. for much of the time. And maybe it's quite simple. Actually, you get, so these enhancement values here, you can still boost by just, this is again with protonated glycerol. So if you go to deuterated glycerol, then at least for this molecule here, which is acetate, we get something like 3-fold higher enhancement. So maybe now we can routinely get 2000-fold enhancement. Then indeed, we wouldn't need to go via carbon. But of course, this would also only hold true if we can record all the information that we want very quickly. Because if we don't have carbon anymore, then we can't retain the polarization for a very long time anymore.
There is another question from Asif. Could you explain again why you had to freeze the bullet outside before loading it into the polarizer?
Yes. Okay. So actually, first we tried not to. So first we tried to just fill the bullet. So we would fill it. And then the idea was that we would sort of gently lower it into a nitrogen dewar. So there would be a tube sitting in a nitrogen dewar. We built all these things. And then we would maybe have a stream of gas that would keep the bullet in position or just slowly lower it into the nitrogen dewar. That was the idea. But what happens is the bullet then sometimes attaches to the wall, and then it doesn't move, and then you reduce the pressure of the stream further and further, and then at some point the bullet comes loose and drops. And actually, at some point, Karel showed me a little experiment. He took a bullet, he filled it with liquid, and he dropped it from a height of 1 centimeter. And this drop from a height of 1 centimeter was enough to cause a spillage. Okay, so when we've seen that, then we decided, okay, no, we don't do this anymore, because of course, when you have that, then you always get like your sample contaminates your entire system, and very quickly you need to warm up everything and clean it and do it again. And so these ideas to move the bullet with the liquid and freeze it only later, they really never worked. So we're not looking back to that. Yeah.
There is another question from Balvinder. So Balvinder, thank you for the interesting and explanatory talk. So he's asking how much time it takes to optimize your sequence and everything for a new sample if it's not labeled, and which other molecules other than pyruvate has been detected with lower limit of concentration.
Yeah, so I think, so historically it took quite a lot of time. So for example, the work that Pooja did, we started first, we knew that we need something to facilitate spin diffusion, and then we added first acetate, and that didn't really work very well. We now believe that the acetate actually likes to aggregate in the sample, so it doesn't distribute evenly. But that was a process of, yeah, okay, then, you analyze the data, and then you think of something else. And like in hindsight, it has taken a few months at least to come up with a good sample formulation. Now, when this machine works, and so it's actually only been working for 2 months or so. So it was in December that this thing started to work properly. Then, of course, you can progress at a much faster rate, and actually the sample preparation and data analysis become also time-limiting steps. Yeah, but of course, still, I mean, you also need to process the findings in your head to then take the next step. So it's not infinitely fast. Yeah, but I think so. The data, like all the other data, that from the autoloader, that's all been recorded within 2 months. So there's good progress. Yeah.
There is a question related to this loss of polarization during the transfer. So Katz is asking, do you think it could be due to the current, and what will be the mechanism affecting this polarization decay? And yet, does it plateau beyond some current?
Sorry, the first part was whether it...
Yeah, so there was a first question. Do you have a hypothesis or some idea as to the underlying reason for the behavior of enhancement versus the tunnel current? That was the first question, actually.
No, well, we don't yet. We did some analysis of this relaxation for trityl. So that's a narrow band radical, and there at some point we felt that we understand what's going on, but we haven't done that in any detail for these temporal samples yet. Yeah.
And so, as
of course, what we believe is, I mean, with the tunnel, yeah, if we go up to at latest when you go up to 10 Tesla, and if the sample stays cold, then it should retain the polarization, right? So yeah, this would be an avenue to explore. Yeah, but it's not so trivial to increase the field really everywhere. Of course, we also have a permanent magnet that you can put somewhere. I think actually, well, yeah, maybe there's some work in the field by Andrea Capozzi and others to put permanent magnets also into the superconducting magnets, because that's what you need to do. Yeah, it's already inside the superconducting magnets that the field drops to very low values, and that's where you need to put your magnets.
Mm. And related also to the transfer, how much polarization is lost as a function of concentration during the transfer in the channel? Do you have a value?
Okay, so I think if we have now a proton enhancement of 2000, that I think translates to something like 8% or so of proton polarization. So whatever else we had before, we lose. Yeah, and proton polarization levels in the solid are also a bit difficult to estimate because you have background signals and so forth. But I think a number of 80% wouldn't be unreasonable. So it's still like you lose a lot. Yeah.
Okay. There are 3 more questions. So the first one from Adam Gaunt. Did you do any optimization of the pulse sequence for polarization transfer to proton from carbon? And further to this, do you see a water signal from exchanging protons? And if you expand the range of molecules, would you have to adjust the sequence to tolerate varying proton exchange rates?
Okay, so this sequence is for methyl. So it's a transfer from carbon to methyl protons. So they wouldn't exchange. We did, of course, yes, we did optimization. There have been studies of this kind before. There's a paper by Malcolm Levitt and Kevin Brindle. They used a different carbon, but transferred also to the methyl protons in the end. Yeah, you can do all these things. You just take a lot of pyruvate, you do everything at ambient conditions, you optimize your sequence, and then you move on to the hyperpolarized experiment. Yeah. Maybe water is of course a problem when you work with really low concentrations. You want to really open your receiver gain, and so you need to very carefully suppress all the signals that you don't want to see. So that would be water. But if, for example, we have let's say DMSO in there at high concentration, or glassing agent, glycerol, or so, we need to be sure that we don't have these things saturating our receiver. Yeah.
One question about the robustness of the automatization of the bullet-DNP. So what is the reliability of the entire automated process, and how many runs before you require human help?
Yeah, it's a bit early to say. When this machine started to work, my recollection at least is that it basically kept running for weeks. And I think we went well over 100 samples before we had to do anything. But then came the Christmas break, and we needed to restart the system, and we had a few issues then. So basically, there are lots of sensors on that system. But for example, what happened a few days ago was that the pressure in the drive unit was a bit too high. And then one bullet was traveling a bit too fast, and it got jammed in the injection device. And then the system now recognizes that the bullet didn't come out, so there's a detector there as well, and then it stops. But then basically someone needs to come in, have a look, clean it, and yeah. And so right now it hasn't done another 20 experiments, but it seems to be, once it's running, it has a high chance of keeping on. Yeah.
Cool.
It's a prototype.
Almost a product to sell. No. Okay, the final question is from Azif. It's interesting. Could you compare the efficiency and the cost of pyruvate hyperpolarization using power hydrogen and that using bullet dissolution DNP? Which technique will be the winner, according to you?
Well, I don't know. What I will say is that in my view, the cost of the instrumentation is maybe not so relevant. If you really think of clinical application, then whether your DNP system costs 500,000 euros or your power hydrogen system costs 50,000 euros, that is on the cheap side. I don't think that matters in the end. I think what matters in the end is more the process. So if you have cheaper materials or cheaper sterile procedures with one technique compared to the other, then I could imagine that makes a difference. But how this will pan out in the end, I don't know.